security by the numbers today? Who went to the keynote? All right. So we're going to carry on a few of the same themes that were covered in the keynote. Remember how Jeremiah said, remember how old SQL injection is, goes back to 1998. I want to start and go back even a little bit further than that, just for a little context set. In 1972, the U.S. Air Force hired a man named James Anderson to do a computer security study. And Anderson was a former gunnery officer, he was a radio officer, he did a number of things, became good at cryptography, and over the period between when he left the Navy and we got hired for the Air Force to do the study, he had become sort of an established expert in computer security. The goal of the study was to determine whether you could build a system that could meet all the classified security needs of the military airlift command without redesigning a completely new operating system. And so Anderson pulled together a team of people from academia, from industry, government, and they spent 6 months together and came up with this report, 140-page report called the Computer Security Technology Planning Study. And you could argue that this study defined the direction of computer security research for the next decade, at least, maybe longer. They came up with a number of attack vectors that became real attack vectors in software. And they predicted a lot of those things very accurately before software was really being produced at a large scale. The reason I like this paper is because, to my knowledge, it presents one of the very first technical descriptions, if not the first, of a buffer overflow vulnerability. And I'll show that to you. You can see what they're talking about here is the code performing a particular function does not check the source and destination addresses properly, and that permits an attacker to inject code, which will seize control of the machine. This was in 1972 that we knew about the existence of buffer overflow vulnerabilities in software. And of course, we've had a number of different software vulnerabilities since then. But this goes back far. We've known about this. And so there it is, black and white, 1972. And I guess you could say that software security has been terrible ever since. So this is one of the many pieces of software security research that kind of led us to where we are today. And that's what we'll be talking about, the state of software security in 2016. Where are we now? Just very quickly about me. I've spent almost my entire career in application security, first on the offensive side and then on defense. I came to Veracode about 9.5 years ago, where we focus on defense and scanning applications, helping our customers find vulnerabilities before attackers do. All of the information, almost all of the information in today's talk comes from a report that we released called The State of Software Security. We're on our 6th volume of that report. And the way I like to describe it is, if you're familiar with Verizon VBI or some of the other reports that are out there that talk about breaches. We talk about vulnerabilities in our customers' software before they get breached, hopefully. And the other reports talk about after they get breached. Now we have a lot of data. We have over 1,000 customers, and we have in this report, the data collected in this report comes from over 200,000 application assessments that we've performed over an 18-month period, from mid-2013 to the end of 2015. We're scanning applications at a tremendous pace, one every 3.9 minutes on average. So there's a lot of data in there. It's anonymized, of course. We break it down by industry, but there's a very, very rich segment of data there. And because we have this, we're in a unique position to be able to report on what's the state of application security today. What does it look like out there? This is a tweet from our chief scientist a little while ago. If you read it. So some might say that this is also just an accurate description of the state of software security today. It kind of captures that that tension between security and developers. But if we just stop there, then this would be a really short talk. So we're going to talk about data. Before we do that, I want to talk about biases. And I think this is not covered often enough. With any data, with any report, it's important to understand the methodology, where the data came from, what are the mistakes in the data, what are the assumptions, so that you can kind of frame your interpretation of information. So I want to talk about a few of those biases in our approach so that you're able to not draw the wrong conclusions or not be led down the wrong path of interpreting what I showed you. Okay, so any study of vulnerability data from any security company out there, whether they tell you or not, has a selection bias. What does that mean? Well, our data comes from our customers. So, like I said, there's about 1,000 plus of those, but there's also good people that are not our customers. We can only analyze the stuff that they send us, the stuff that they're producing. Some of our customers have 2,000 to 3,000 applications. They may only send us 500 of those. So we have a selection bias inherent in what they choose to send us, as well as who they are. You could say that this kind of shows the best possible scenario of the state of software security, because we're talking about companies that actually care enough to invest in the process and scan their applications, whereas there are many companies out there that are doing nothing at all. Another bias we have is experimental error. So when you're scanning software, whether it's static or dynamic or some other form of technology, you're going to have false positives and you're going to have false negatives. False positive is when you detect something that turns out to not be a real problem. A false negative is when you fail to detect something that actually is a problem and the technology just doesn't find it. So of course there's going to be that. Whether it's a human, whether it's an automated tool, there are going to be things that are flagged inadvertently and there are going to be things that are missed. And that's just something that's baked in. You have to assume that that's going to be there. It doesn't make the data not valuable, but just keep that in mind. And finally, capabilities bias. I don't really have a term for that, but we choose as a company, Veracode, how deeply we want to go into each language, each framework, how good we are able to afford to make our capabilities in different areas. And so of course that factors into it as well. If we just launch support for a new language, for example, at the end of that window, and that language is going to seem better than it actually is because we don't have as much data around it, or we may not be as deep in detecting those vulnerabilities. I know this is weird to kind of be starting off by, here are all the things wrong with it, but I don't see it often enough, and you really do have to know. And here's biases in interpretation, how you may think about this. Drawing conclusions that may be convenient but incorrect. So two examples I'm going to give you there. We've got a lot of applications. Like I said, some customers have hundreds of thousands of applications. When we don't know everything about those applications, how old they are they under active development, what the team size is, what the how good the developers are, all those things, we may conflate a lot of different things together. Right? We're blending results from lots of applications together, and we don't know much about the application maturity. So we may be tempted to draw some conclusions there. The attribution bias, saying, well, this industry did very badly, so all their developers must be really terrible. I mean, that may be the case, but it's not necessarily borne out by the data. So we don't want to make those kind of assumptions either. We can try to guess why things happen, but we don't necessarily know for sure. Answering the why is very hard. What I'm going to give you is the what. I'll say this a number of times, that remember correlation is not causation. This chart just reminds you that you're not going to reduce the number of Nicolas Cage movies by erecting fences around your swimming pools. There is a correlation between the two, but there is not a causation. Make sense? Everyone knows this. So we're going to start by looking at how different industries compare against one another. We use industry definition from data.com, which in turn comes from the Bureau of Labor Statistics. If you look at the BLS, you'll find about 50 or 60 different industries represented in that data set. And we don't want bar graphs with 60 bars on it. So what we've done is we've collapsed a lot of those industries together. So for example, we have a group called technology, and that would include things like software and electronics and telecom and so on. So what I'll be showing you is those kind of rolled up industries that originally came from the Bureau of Labor Statistics. Okay, so who does best against industry standards? And for this, we use the OWASP Top 10 as a definition of industry standards. It's one choice, but you do have a lot of web applications being scanned. Probably half to two-thirds of what we scan from our customer base is web apps, so that's a good place to start as any. And when we talk about failing an OWASP Top 10 policy upon initial submission, what we're saying there is, how many of these applications had at least one flaw or vulnerability? I'm going to use flaw and vulnerability interchangeably. How many of those applications had at least one flaw that fell within the OWASP Top 10 taxonomy the first time it was scanned with us? And this is what you end up with. It's actually not a huge variance between the worst and the best. You have 76% failing in government on initial submission and 58 in financial services. So it's not a huge range. This is the same data kind of presented the different way. So everybody else is kind of grouped somewhere in the middle. This is only one way of looking at the data, obviously. OWASP Top 10 is one lens to view that. Some industries may not have as many web apps as others, so OWASP may not be as relevant to them. But generally, it's a good, with that amount of data, is a reasonably safe choice for a taxonomy. What you should really take from this is that even the best performing sector, which is financial services, is failing for 3 out of 5 applications. And if you've worked a lot with the financial sector, you know that they do tend to be ahead of the curve in terms of technology adoption, in terms of maturity, of process, of tools, and all those things. And they're still doing fairly badly against OWASP Top 10. This is really awful. Show of hands, who thinks flaw density, which is flaws per megabyte, flaws per 1,000 lines of code, flaws per some unit measure, is a valuable thing to measure? Anybody? It's not a trick question. 2 people think it's valuable. It actually is, but not in the way that a lot of people use it. So a lot of our customers and analysts and reporters and everybody who knows that we have this type of data will ask us to measure, to report on flaw density so that they can say things like, this language is awful, or, you know, this industry sector is terrible. What is wrong with manufacturing? And that's a misleading metric. The reason is because the programming language itself has a significant impact. There's some language that you can accomplish a lot in a very little bit of code, so therefore your flaw density is going to be higher. One example. Who's seen this cartoon before? I know it's trendy to hate on XKCD, but I like this cartoon. The point here is the guy's flying, and it's like, oh, how did you do that? You know, it's like, oh, I used Python, import anti-gravity. So the idea is there you can do a lot in very little code in Python, and you can imagine if you were trying to implement anti-gravity in Java, it might take you 10,000 lines of code instead of 1. So that impacts how you report on flaw density. So back to the chart. Some languages, like C and C++, produce compiled code that's really, really high density. And that means that any industry or organization that uses a lot of C or C++ will have a higher prevalence of those denser, higher flaw density because of the prevalence of those languages. So I'm giving you these industry comparison numbers around flaw density, and I'm immediately kind of telling you, don't read too much into it. I'll show you later when we want to use flaw density, where it is valuable. It's not here, but we have the data. I mean, do you really think that manufacturing is 23 times worse than healthcare? They might be better, but I really don't think there's that much of a difference. So this is what we ended up with. And on the right there is just the flaw density for very high and high severity flaws only. So again, when you read something in an article or anywhere really, where they're talking about flaw density, and if they report that manufacturing or technology is really bad like that, just kind of keep that in mind. It really matters what types of languages they're using to produce their applications, and that has a much more bearing on those numbers. Flaw density is useful when you want to track over time the number of flaws or the flaw density within a given population. So for one application, for example, that I'm building, what's my flaw density today versus what's my flaw density a year from now? That's valuable. It's the same application. I'm not conflating any other factors. If I have 100 applications and I compare the density of those same 100 applications a year later, that's useful. So you want to use it to track over time, and we'll use that to talk about remediation rates later. Finally, as far as industries go, I just wanted to show you a prevalence of a few vulnerability categories across different industry verticals. Now, SQL injection and cross-site scripting have consistently been at the top of the list for AppSec flaws. Cryptographic issues are on there because they've been highlighted in recent years as being relatively important. Things like Heartbleed, things like some of the mobile vulnerabilities that come out, and we'll dig into the mobile stuff a little bit later. You may notice that the numbers here are kind of different from what you saw in Jeremiah's talk earlier. He had SQL injection around 6%, cross-site scripting
lower than we have it. And again, the disparity for that is because of the analysis type. We're looking at mostly, we have static and dynamic in there. They have mostly dynamic. We're looking at internal applications as well as public facing. They're looking at public facing only. And so that's, both are actually correct. But, so again, keep in mind when somebody says, only 6% or 40% of applications are vulnerable to SQL injection, think about where that's coming from. Excuse me while I resize some of the panes here so I can see my notes. So again, SQLi, cross-site scripting, who's the outlier there? The light blue line is government. So they're kind of standing out as being significantly worse in those categories. Cryptographic issues are a slightly different picture. You have healthcare out there, far right, 80% of healthcare apps being impacted by at least one cryptographic issue. And the rest kind of cluster around the middle there, with manufacturing kind of being the best. Again, there's a lot more data than this in the full report. I wanted to call out these particular examples because these are categories that we're all familiar and interested in. Now I want to slice it differently. So we sliced by industry. Let's take the same data set and slice it by language and see if there's anything interesting that we come up with there. So first, just an understanding of the data set. And there's not really going to be many conclusions that you can draw from this chart, but I just wanted to show you over the years, as we've done multiple volumes of this report, and of course, the number of applications has increased over time, but also the language distribution has changed over time. And this is mostly enterprise and mid-market, so not a lot of very tiny software development shops here, a lot of enterprise and mid-market. And what you basically see from this, really the only thing to take from this is that .NET appears to be on the rise in enterprise development. I would say that's about it. So even though we've added a lot more languages that we've supported in our most recent analysis, you still see .NET increasing as a percentage share there. So I don't know if that's surprising to anybody or not. It's not super surprising to me, although you might think enterprises would start moving towards, I don't know, more, not more modern languages, but more interpreted languages or some of the trendier languages that you're seeing. But no, .NET is on the rise. Question?
Well, do you think that's also, or could that be that as you've gotten more clients or new companies coming on board, that they've always been .NET shops, or is this based on, I guess?
Yeah, the question is how much is it a representation of our customer base? Yeah, that all factors into it. I mean, the fact that you have a lot of customers smooths that out a little bit, but certainly, even if you bring on a new customer and they have 2,000 .NET apps, that's not going to move the needle very much, right? So, but yeah, that's why I kind of started with that. Yeah, there is a selection bias. If you went back about 10 slides ago, you remember we compared industries against their initial pass rate against an OWASP policy. And here we'll do that again, except sliced by language instead of by industry. It's not surprising that C and C++ had a higher pass rate because you don't really use C and C++ to write web apps very often. Some people still do. And there are some vulnerabilities in the OWASP top 10 that can appear in non-web applications, which is why you do still have a 40% fail rate there. OWASP is not the best fit for mobile sort of client-side applications, but they're in there anyway. My only conclusion from this that I can really draw from this, I think, is that scripting languages need help. And I'm including classic ASP, I mean, any legacy language really, but classic ASP, PHP, Cold Fusion are really, really, down there near the bottom and doing really, really badly. Prevalence again, except by language. Now, again, you see that SQL injection, cross-site scripting are significantly more prevalent in applications that are written in web scripting languages like classic ASP, Cold Fusion, PHP, compared to .NET and Java applications. .NET is in the sort of the dark pink and Java's in green, dark green. And so these are not really surprising. Maybe the numbers are surprising because, again, when you compare them against other reports that are being drawn from different data sets, different types of analysis, you do see drastically different numbers. We're still seeing SQL injection around the 30% mark of all applications. So again, the application having at least one occurrence of that flaw. Cross-site scripting, again, significantly higher, into the 40 to 60% range. And remember, when I say at least one, sometimes at least one means 1,000. We can guess as to why this happens. There are fewer secure APIs built into some of these older languages. I don't even think there's a way to parameterize queries in classic ASP. I'm not positive. There's certainly not very many encoding mechanisms built in. Cold Fusion didn't start packaging eSAPI with the Cold Fusion release until maybe 5 or 6 years ago. The language has been around for a decade and a half, maybe longer. PHP, even up until PHP 4 or 5, you couldn't do, there was just no way to do security things properly. So you'd have to roll your own, or people just wouldn't do that, or they'd do it wrong. Whereas .NET, it's pretty mature. Java is pretty mature. There are good options there. So I think that's kind of why you see that. Question we get asked a lot is which application technology is most secure, and so, there's no real answer to this. The way to read this chart is, again, you've got your programming language distribution shown in the bars, and then the number out on the right there is the rank order of what we showed at the very beginning, like which industry was doing the best in terms of pass-fail against the OWASP policy. So what I'm showing here is that there's no rhyme or reason. There's no like, oh, well, number one clearly just has, none of this type of language, and the worst one has all of this other type. It's not like that. It's all over the place. Look at manufacturing. There's, they're number 2, and, they're kind of bucking that trend towards the Java.NET dominance, yet they're still doing, number 2 in terms of pass-fail rate on that initial submission. So I think that if there's any inherent security disadvantage in language choice, it can probably be overcome with process and program and things like that. That's all I can really take from this, because I don't see any direct correlation between language choice and how well the industry is doing based on the data that we have. So this is my takeaway, and I can't necessarily prove that, but it's how I think the data can be explained. This is the deepest that we'll go in terms of flaw categories. You can see here that we actually have individual CWE flaw categories broken down instead of just generalized descriptions. But there's a lot of scrutiny on mobile these days, and certainly on privacy and security. And these numbers always surprise me a lot, even though we get roughly the same every time. This is a breakdown of crypto flaws in mobile apps only, so iOS and Android apps only. Insufficient entropy, not using the right random number generator. Okay, that's not surprising. Not as impactful. A lot of the times they're just using that random number for something that's not security critical, so I'm sort of not as alarmed by that one. The second one on this list is really alarming to me, and that's improper validation of SSL certificates. So you have a mobile app, it connects over SSL to a server, and it intentionally does not validate whether that server certificate is valid, whether the host matches, all those things that you're supposed to do to make sure that not only is your traffic encrypted, but that you're talking to who you think you're talking to. 50% do not do that correctly based on what we've seen, which is crazy. I have anecdotal evidence for what's happening there. We've asked some developers, oh, we turned that off in QA and we forgot to turn it back on. We hear that a lot. I don't think it explains all of it, but it's kind of annoying to have to go cut a specific cert for your QA server, which has a different name than all the other servers. And it's not that it's expensive to do, it's just that it takes time and it's another logistical thing. And then they forget to turn it back on. So these are the ones that are interesting but less interesting to me. 297 is crazy, I think. Okay, so there was a lot of charts and graphs. I'm going to give you 30 seconds of cats in various stages of code development, and then we're going to get back into the graphs. These are from the internet. This cat appears to be working on some sort of fluid dynamics simulation. This cat is obviously waiting for his code to compile. This cat is getting started with coding, but realizing that C++ is a really, really terrible option these days. All right, now we're back awake again, back to it. Remediation profiles. Jeremiah raised this point in his talk, which is you can find all the stuff you want. If you don't fix it, what is the point? What are you doing? So we've talked a lot about what we can find, and now we're going to talk about what's getting fixed where. Something I'm really proud of, we have this data across all of our customers. We found in 2015, we detected nearly 10 million flaws across our customer base, and we know definitively that they've fixed across the customer base, they've fixed nearly 7 million of those, which is really cool. I don't know that anybody else has that kind of statistic on that wide a scale. Now that still means 3 million or not, but some of those, again, they may be things that they don't agree with or they have mitigating controls for or any other reason, but still, we know that 7 out of 10 million, they're like, yeah, this is real, I should fix this, I'm gonna do it. And we can verify that they did that. So that's kind of cool. So industry slice again. Who does the worst, who does the best? Now here we have a much, much wider discrepancy between the best and the worst. Are you surprised at all that it's manufacturing that comes out on top? 81%. They remediate 81% of what they find through us. And then, of course, the other end of the spectrum is the government. We find a lot. They fix 27% of it. That's not so great. This is the same data. And so there's a huge disparity in terms of what's found versus what's fixed. And again, if you're only finding stuff, you're really not moving the needle at all. You're not making yourself any more secure. You're not raising attacker cost. You're not doing anything except being aware that you have more exposure, which is okay, but doesn't really help. We were trying to think about why would manufacturing be so much better? And again, I don't have a definitive answer, but I think if you think about how manufacturing works and the history of the industry, they have a lot of regulatory drivers. If you think about how they manage their supply chain of parts and things like that, logistics, they have process improvement built like very, very tightly into their culture. They may have just better policies around setting achievable goals. I don't know what it is. I do think that rigor around manufacturing and operational efficiency and just always trying to figure out how to getting better at getting better is something that is not unique to manufacturing, but is certainly prevalent there. Maybe more so than it is in healthcare or government. I don't know, was there a comment?
Well, who is government? Is local, federal, DoD?
Government. The question is, who is government? Government is any government. So federal, state, local.
Yeah, DoD there as well?
That would be included in federal. So again, it's only a slice of the customers that we would have from the various agencies. But it's all kind of blended together. Excuse me. So remember, correlation is not causation, again. We wanted to look at what is the impact of remediation coaching. So one of the services that we offer to our customers as part of their subscription is the ability to do a scan of the application, but then also have somebody do a readout, which is common in the pen testing world, but not common in the automated analysis world. In fact, we may be the only ones that do it. The idea there is you take an hour, you have somebody walk you through the findings, answer some of your questions. Oh, what is this type of vulnerability? Oh, what is the impact of that? I'm thinking about fixing it this way. You have a discussion basically between a security expert and a developer, and then they go off and they fix some issues and they may go rescan or whatever, but they've had some consultation time with somebody. And we found that the impact of remediation coaching on flaw density for a given application, so again, only looking at one application from point A to point B, from scan number 1 to scan number 2, is significant. We saw that when there was a readout, they reduced their flaw density by 42%, which is not great, but it's still better than 17%. There's a long way to go. But that's a 2.5 times difference. Is it because they had a readout? I don't know. I would like it to be related to the fact that they did a readout, but it also may be that companies that require developers to do readouts also set a higher bar for security. They may have stricter compliance regimes. There may be other factors at play here, but there is definitely a correlation between having a readout and reducing your flaw density and basically remediating better. So that was interesting to us. Remember, correlation is not causation. Another thing we sell to people is CBT-based e-learning, slideware for various topics. And we thought it'd be interesting to measure the impact of e-learning on remediation rates. Basically, does the customer have that or do they not have it? And how does that look across their application portfolio as a whole? Now, there's a lot of factors here, but if you had an e-learning subscription, you fixed 75% of the stuff that we found. If you didn't, you fixed 58%. Again, these are averages. And there are a lot of other factors here. Again, some developers, like, you might have an e-learning subscription, and your developers might not use it. One developer might use it, and the rest might not, right? The fact that you have an e-learning subscription may also mean your AppSec program is much more mature than somebody else's. Okay, so there's all these other factors that kind of play into it. I would like to think, I have always wanted to be able to prove that training, e-learning, whatever form it took, would improve code security. I don't think anyone's been able to prove that yet. There is a correlation, but just in case you didn't get that, I didn't make the claim that security training results in more secure software. I know it's a very contentious thing. And the last thing, we just want to look at fixed rate by analysis type. So I mentioned we do static analysis, dynamic analysis. We even have pen testers that analyze applications in the traditional way that you're familiar with. And we did find that remediation rates were highest for static analysis. Not a huge amount higher. We think that that probably has something to do with the fact that static analysis, you get line of code, file name, you get pointed to the exact root cause of where the flaw occurred. Whereas dynamic or a pen test, you have to figure it out if you're a developer. Now, you know the app pretty well. You'll probably be able to figure out. But with static, we point you right at where it is. This is where you make the fix. That's my best guess there. So we did see a little bit of a variance there. So this last section isn't directly related to the study, but I wanted to include it as a takeaway because I know that a lot of people here are responsible for software security at your own company, and I don't like to just throw a bunch of data without also giving at least something to take away. So this stuff is not in the report. I'll give you a quick story again. Around the time of World War I, only 7% of American households owned toothpaste. And the Army had just enacted the draft at that point, and they were finding that so many recruits came into the Army with terrible dental hygiene that they actually declared poor dental hygiene a national security risk. Think about that, World War I. Okay. Around the same time, elsewhere in private industry, a man named Claude Hopkins was hired by Pepsodent toothpaste company to design a national ad campaign. So he had to find something that would make people want to brush their teeth more often. Remember, 7% of households own toothpaste. So he went, he read dental studies, he read textbooks, he read all these things in the dental literature, which must have been thrilling. And he found something he could use. He keyed onto this thing called mucin plaques, which is just a film that accumulates on the teeth over time. And he renamed that, he flashed onto that, and he said, oh, the film, the dingy yellow film, like, that's really gross. And he kind of appealed to the public's narcissistic tendencies by reframing Pepsodent not as a healthcare thing, but as a beauty aid. And what this did was to define a simple cue and a behavior and a reward. So the cue was, oh, everyone's got this film developing on their teeth. That triggers, well, I should brush my teeth. And the reward I get for that is, well, I'm going to be prettier, according to these ads. Within weeks of these ads going out, Pepsodent couldn't handle the demand for the toothpaste. Within 3 years, they were an international product. And within 10 years, 65% of American households owned a tube of toothpaste. And the US military downgraded that dental hygiene as a security risk thing. It was a great marketing success story. But what does it have to do with AppSec? I think that we have to start thinking like Claude Hopkins, the marketing genius. I mean, we're doing marketing to a certain degree. We have to think about that in terms of getting developers to build habits around application security in the same way that he tried to get them to build habits around brushing their teeth. Whether that's remembering to scan your code base every night, or whether it's simply following a security checklist every time you launch a new feature, whatever it is, a daily task or a routine task is going to be something that's more habit forming than, let's say, a security activity that happens once a year like a pen test. If you could raise the level of security hygiene in the same way that you raise the level of dental hygiene, that would be really, really amazing. We all know that security hygiene is not really that great right now. But the fact is, this was successful because it was habit forming. It got in people's heads, and they just got used to doing something. You wouldn't even imagine of not brushing your teeth today. So I don't have a one-size-fits-all approach about how you apply this to security today, but I do know that you have to think about your culture, the moving parts in your organization, and figure out where you can get developers to form habits. We already touched on this, but the fact that if you're only focused on how much you can scan as opposed to how much you're fixing, you're really not doing much about the problem. It seems silly to say that they have to remind people that remediation should be a focus of a program, but in many cases it's not. In many very large organizations, they're much more scan-focused than remediation-focused. And so how do you make that push? Maybe you mandate a readout for every scan. Maybe you have better office hours for your security group so that it's less difficult for a developer to actually make that change. You lower the barrier to making fixes. So again, it depends a lot on the organization. Maybe you import all your security bugs into the same bug tracking system that developers use to fix all their other bugs. So they've already got a habit around that, right? They check, right? So queue behavior reward, right? You check Jira every morning or every hour, however often they do it. Your behavior is you fix some bugs, whether they're regular QA issues or whether they're security bugs. And then your reward is you get to mark the tickets as closed. Developers love to mark tickets as closed. And so that's a good way of kind of getting a habit formed around remediation as well. The last one is just remember to measure. If you don't, Peter Drucker is kind of given credit for being the founder of modern management philosophy, and this was one of his many quotes. The idea is if you're paying attention to something, it's actually going to help you improve in those areas. Unless you're kind of actively sabotaging it, you're going to improve if you're measuring. So it's sometimes hard to see minor progress subjectively. But if you're measuring it, you can take credit for it. If you got 1% better or 5% better, you may not notice that unless you're actually writing it down and measuring it. So number 3 is kind of measure early and measure often. So I'll repeat those 3 takeaways. So number 1 is form habits. Find a way to form habits. Get the developers to form habits. Number 2 is focus on remediation. And number 3 is create metrics. So that's the takeaway I want to leave you with. You can get all the information that I presented, plus a lot more, in the State of Software Security report on our website, veracode.com. That's all I have to present to you today, but I'd be happy to take questions if you have any. Right there in that.
So you talked about the federal government being kind of the worst case in terms of remediation. I was wondering what you're giving me. So one of the things that we've noticed, like I work for a company that's a software vendor that sells to the federal government, and they are probably the most strictest customer we have in terms of how quickly we respond, and they kind of hold us to the letter of the law with respect to our support policy in terms of fixing vulnerabilities, or remediating vulnerabilities. So in other words, I kind of see them as the toughest customer for us, but
why the disparity?
Why are they not remediating?
Yeah, well, we don't always practice what we preach. They may be government is more mature. Government and manufacturing, I think, are kind of more mature in terms of how they think about software supply chain. We've seen that, and that's what you're experiencing, right? As a vendor, they're saying, well, you have to do these things before we will accept your software, until we'll approve this contract or whatever, right? That doesn't mean they're doing it for themselves. They have a lot of legacy software. They have a lot of applications that are built 10 years ago, 15 years ago, that are still being used for business critical things, but there may not be any developers against them. A lot of times it's not that they don't want to fix it, it's they just don't have the resources to fix it. We don't have any way to gauge that, right? I don't have a query I can make that can answer that, but anecdotally, yeah, we know that they don't recycle it, they don't develop at the same pace and with the same intensity that happens in the commercial space, and they hold on to things for a lot longer. So that's my best guess.
Right, so you're saying because they move really slowly on upgrading and those kinds of things, they might have good requirements in terms of mature requirements, but they actually don't know they don't have the mechanism to implement.
Yeah, I think a lot of that is it. And they also may have a lot stronger vetting process before, like, to clear something for an upgrade, which is, I think, plays into the patching thing as well, right?
Yeah.
You got to do it. You got to make sure nothing fails in any particular way, and that just draws out the testing cycle. Whereas, you know, a software shop, a software vendor that's doing like DevOps or Agile Scrum, they'll do the fix and then they'll push it out in the next sprint, and it'll be done in 2 weeks or a week or whatever. So yeah, I think it has a lot to do with that.
Thanks.
Yeah. Any others? No.
Hi, so I had 2 questions. So number one was, you know, you're doing the results of the readouts had, you know, better fixed rates. Do you guys intend to ask your customers to do this and measure if there's an improvement after you ask them to implement a system like this and see if it, you know, you can actually get a direct correlation?
Well, so what we showed actually was that is what we showed. Now, what we're not able to do, we're not able to make the causation argument because it's impossible to isolate all the other factors, right? It's impossible to run this sort of controlled experiment without significant, like, customer
I guess the
cooperation,
idea was
I guess,
you
right?
go to ones that you know aren't doing it, and you ask them to do it. So, I mean, you can't make nothing else change, but ideally they weren't doing
Right.
it before, and now they are. And
Well,
then
and that's
6
what-
months
yeah.
you try to measure a difference. You know.
And that is what the data shows. I mean, the 2.5 times improved across the board. But we just don't know if there are other program maturity things that factor into that. It's difficult to isolate.
Okay. And my second question is, you're showing how you knew like about 10 million vulnerabilities and about 7 million got
Yes.
fixed. So the 3 remaining ones, are they like 70% of those are government because they don't remediate as fast?
Right. So I don't have the breakdown on what was not fixed. You can probably extrapolate that pretty closely. What you find in those 3 million are a higher prevalence of the low or very low severity flaws. So you certainly see companies fixing the high and very high severity things faster, which you would expect. They may just not get to the lows. They may decide that the business criticality of the application or the worth of the data that's being stored by the application is not worth the cost of fix. There's a lot of reasons why people choose not to fix things. It does tend to be the lower severity things. Maybe the application is going to be end of life. Maybe, you know, there's a lot of reasons. And then some of the things just may be issues that they choose not to fix in the code, but they choose to fix by some control that's outside of the software itself that we can't actually see. So when we scan it again, it appears that, you know, the flaw is still there, but let's say maybe they put in a specific blocking rule in their WAF to prevent that attack or something like that. So we wouldn't see that it's fixed, even though from their perspective it is fixed. So that's about the amount of visibility that we get into, you know, into the remediation patterns. Okay. Is there over there?
You know, you said with remediation coaching, you couldn't tell for sure if it was helping.
Yeah.
Have you ever had the case where you had a company 1 year they didn't use it, and then the next year they started using it and compare the 2 years?
Right. We don't have any cases quite as clean as that, unfortunately. That would be awesome. Usually what happens is, as we onboard a customer, we push really hard for them to do readouts for at least their first few times through, just so they understand what's available to them. But so to then say, like, all right, stop doing it for a year, stop doing it for 6 months, and then start doing it again is kind of, it would at least appear to be not in their best interests, and they would just be the guinea pig, but like, what would they get out of that? We would get great data out of it, but I think it would probably not be the best advice that I could give them. Okay, was there one more? Do we have time? Okay, yep.
So I have a quick question. So how do you know if they fixed the finding or not?
How do we know if they fixed the finding or not? Well, basically, when we do an analysis, we're doing a whole program analysis, and we're looking for particular patterns in the code. So for example, a SQL injection, we'll see a piece of user-supplied data. It'll traverse through the application, and eventually it'll get to a database call when it's used in an insecure way. So if we scan it the first time, we see those patterns, we mark all those patterns. If we scan it the second time, we don't find that again, we can correlate, you know, the first set of results with the second set of results. Anything that doesn't show up the second time, we assume to be fixed. Anything where the pattern doesn't flag again. So that's what we're using to determine if something's fixed. We don't detect it anymore, which is mostly accurate. All right, that's it. I think we're out of time. Thank you.